something I think you'll understand.
Good morning, good afternoon, good evening, whatever the case may be. We are back and better than ever.
We certainly are, and we are honoring the great legendary rock band, the Beatles. Because on the day of this taping, it has been 50 years since their appearance on the Ed Sullivan Show. The British invasion started then, changed the world forever. But even more exciting, we are talking about solids of revolution, the calculus. Yes, thank you, Sir Isaac Newton. Thank you, Gottfried Wilhelm Leibniz. Let's do it, shall we? All right, so we are talking about solids of revolution, and how do we produce those solids? Well, one way that solids can be produced is by taking a function, y equals f of x, just any sort of function here, graphing it, and then considering the area between 2 points A and B, and the x-axis and the curve. And we already know how to find that area. We would just integrate that function from A to B, yes? Well, what would it look like if we rotated this area 360 degrees or 2 pi radians about the x-axis? Well, if you can imagine this area rotating and leaving each slice of area behind, you would get a solid that looks like this. And maybe you have a little bit of difficulty picturing that. So I have a couple of examples here. If you look right here, this right here is the graph of square root of x from 1 to 4. Now you can't really see the axes because they're in a cube, but right along here is the graph of y equals root x. And if I click here, it will animate it and show you how that solid is formed by rotating it 360 degrees about the x-axis. And you can pause it, or you can go to this website and you can see these same examples. But you can see how we start here, we rotate it, get back to the top, and we get that nice nifty solid, which is right there. Okay, right there. Let's take a look at another one. This is the function 2 over 1 plus x minus 2 to the quantity squared. I'm not sure what the bounds are, but if you take this curve and the area under it from here to here, bounded by the x-axis as well, and you rotate it, you're going to get that nifty little figure. Nice. You see how it works? You take this, rotate it all about, you get a nice solid area. Okay, so let's go back. I don't know why that keeps popping up. It's annoying. And then here, we're going to rotate 2 plus sine x about the x-axis. And they've started it with that curve just sort of lying on its side, probably because of the orientation of these axes right here. But if we rotate this, I think you can see we'll get this solid. And I kind of like this animation because they leave the opening and then they fill up the solid. Nifty. I'll let it go one more time. Of course, you can go to the website or pause it and rewind it if you want to take another look. But I like this one because what we're doing is we're filling up this solid, which is actually the whole point of doing this. And that is to, I just need to pause this here, get back to our board. We are going to find the volume. We're going to find the volume of those solids using calculus. And how in the world are we going to be doing that? Well, we can use what is called the disk method. So if you look at this, this is the same function that we had before, some generic function, just a little bit larger, and it has been rotated to form this solid here. And what we're going to do is take slices of that solid. And what you end up with are little discs. Okay, you end up with little discs. And to start off with, those discs might look something like this. You can see how it's slanted, and then it would be a curve here, and then up here, and then around here. If you can imagine that, if I'm laying this on its side, it might look something like this, with these sort of curved edges. But the more slices we take, the shorter this gets. Imagine this one here. Oh, that's a bad circle. Let me undo that.
Okay, if I, get really close here, goes around, that's not much better, but I think you get the idea that it would get thinner and thinner and thinner until if you took an infinite number of slices to form these discs, H would be approaching 0, and we would have a very teeny weeny cylinder. Now I'm drawing a big thick cylinder just to illustrate the point here. Again, I can't draw another circle there. There we go. Just to make the point that I want to make. What we're going to do is we're going to find the volume of an infinite number of cylinders. We're going to keep slicing infinitely and find the volume of all of those cylinders, and we're going to add them up. Okay? So, what's the formula for the volume of a cylinder? Well, it's pi times the radius of the cylinder squared multiplied by the height. We know that formula. Now, in this case, we have to understand that the height of the cylinder is actually the width of the slice right here. Okay? And the radius is going to be from here to here, all the way up to the curve, right? Well, isn't this coordinate right here, x, let me erase this cylinder, x, f of x? This coordinate right here, and in fact, this length right here, from here to here, is equal to f of x or y, x f of x or xy. You guys are used to that. So I can find, this is the radius, boys and girls. That is the radius of that cylinder. So I can easily find this height by finding this value of x and plugging it into, I said plugging, substituting it into the function. Okay? Then I square it times the height. And again, if I take an infinite number of slices, then my height is going to get smaller and smaller and smaller. It's going to go to 0. I'm going to find the sum of all of those volumes as h goes to 0, which we know to be, and we've already shown, is really just an integral. Okay? So I can find the volume of any solid rotated about the x-axis by taking the integral from a to b, where I start the slicing and where I end it. Pi times the radius, remember the f of x represents the radius of the cylinder, squared. That's just the formula for the volume of a radius. And I clean it up, I factor out the pi, and I get pi times the integral from a to b of y squared, replacing f of x with y. It really doesn't matter, it's just easier to write this way. And if you're still unclear about the what it should look like, I don't know why that's there. I don't want applications. Let's go here. Here is square root of x. This is a nice animation. Okay, and you can go to this website too if you want. They're going to graph y equals root x all the way out here. Then they're going to graph another line, and I'll explain that in a second. You'll see as it goes. So y equals 1/10 x. And they're doing that because they don't want to go down to the x-axis. They're going to shade in the region down to that line and from 0 to 4. So they're going to shade in here, and they're going to rotate that. Okay? And then they rotate it about the x-axis. And I'm going to pause it for a second just to explain that this is a different than what we're doing right now, but it's a really good animation. And we'll talk about how we find this volume by slicing out some of the volume later. But for right now, I want you to imagine that this line isn't here, and this is just solid in here. It's one big giant solid with no hole. And so we'll continue the animation to see what happens. And they're going to show you taking a slice. And you can see what I was trying to draw before, and they'll tilt it sideways so you can see it. And again, ignore that hole. And you can see how if we took an infinite number of slices that we would get a cylinder. Let's go back, and I'm going to pause it when it comes up. And that is what I was trying to draw over here when I was failing so miserably. Yeah, right in here, right here. Okay. So the upshot is I can find the area of a solid rotated about the x-axis by taking the integral from A to B of pi times y squared. Now, here in the book, they factored out the pi, but on your formula sheet, they didn't. No big deal. Okay, so let's try an example. It's really, really not hard once you understand how we use the formula. So we're going to find the volume of this object, which was generated by taking the line y equals x and rotating it 360 degrees, or 2 pi, about the x-axis from 1 to 4. So the volume equals the integral from A to B, using the formula sheet, which I've pasted right here, pi y squared dx. Okay, so for this case, that's going to be the integral from 1 to 4. I'm going to factor out the pi. And what is y equal to in terms of x? Well, it's just simply the line y equals x. So I'm going to put in x. Very important. It's the function squared. So in this case, it is x squared. Don't forget to square that function. That's a common mistake. Dx. Well, this is child's play for you now, I hope. This becomes pi times integral of x squared is x cubed over 3, evaluated from 1 to 4, which is equal to pi, and I'm just going to use parentheses here, multiplied by 4 cubed over 3 minus 1 cubed over 3, which is equal to pi times 64 over 3 minus 1 over 3, which is equal to pi times 63 over 3. 63 over 3 is 21, so the volume is 21 pi units squared. Nope, cubed, that's volume. Units cubed. Okay, we only have one more short example. I'll put that in another video. I've done all the damage I can do here. I am out!